Okay, so welcome to Chapter 7 webinar here. This is part 3, and we're still in the chapter dealing with gas laws, state changes, solubility, and lipids. So we got through a lot of information in the first 2 parts, and so in this third part, we're going to be talking a lot more about lipids because we obviously have addressed gas laws, state changes, and solubility. So let's get going with it. So the very first thing we need to talk about are oils and esterification. What is this and what's going on? You guys have now known through all my teachings and reminders that the condensation of carboxylic acids generally produces esters. Usually alcohols are combined with the carboxylic acids in order to produce them. Now, there's various different types of alcohol, so it doesn't have to be like a methanol or ethanol. You guys know that even xylitol, erythritol, and even glycerol, really, or glycerin, that's another name for it, is also used in the addition of some carboxylic acid reactions in order to produce the esters in question. So as a nice reminder, oils and fats are nonpolar. Again, we talked about that with respect to solubility, and there were certain medicines, some of the other, and just molecules in general that we take to maybe help our body for whatever reasons, whether it's vitamins or whether it's for, I don't know, ADHD or whether it's for depression, just, you know, different things like that, different molecules for obviously different medical reasons. But some of those active ingredients are then polar and some of those are non-polar. And so, you know, it's necessary to have oils and fats available in your diet or, you know, available whenever you're taking some kind of non-polar active ingredient, okay? Even things like vitamin D, remember, are also non-polar. So for better absorption, it's probably good to make sure that that is added to some kind of food stuff, maybe some kind of drink, maybe something like that that will have some nonpolar interactions, some oils or fats. Anyway, all right, so let's get back going to the esterification process. So the condensation reaction. Here is an example where you have glycerol. So this is a 3-carbon alcohol, right? And this is, I think I remember mentioning to you in one of my demos that the glycerol, or glycerin as it's also known, is a very viscous liquid substance, and you know, it's typically used as a humectant. It definitely adds texture. It preserves moisture in given formulations, and this could be whether it's, for instance, a toothpaste or whether it's some kind of cosmetic. It has really nice textural moisturizing properties that that lend itself to being sometimes a primary ingredient in some of these cosmetic ingredients. Anyway, so you have glycerol here, and then you also have these 3 separate fatty acid chains, okay? And they have the carboxylic acid character. So although we can use carboxylic acids such as just citric acid, which lacks this aliphatic chain, you know, this fatty acid, or this fatty chain length here, whether it's single bonds throughout, meaning that it's saturated, or whether it's unsaturated. For instance, if there's the presence of 1 or even more of the double bonds, each one of those, as the longer they get, they're just termed fatty acid molecules. So you know this because we actually had done the soap lab, and the soap lab didn't necessarily use glycerol and these individual fatty acids, and we'll come back to it. I'm going to revisit this again, but this is almost in the same spirit of what we would be talking about. So actually what you're seeing here with the glycerol, with these individual fatty acid chains, it's almost like all that itself could be considered a soap, quote unquote soap. So that's definitely a possibility. So in a condensation reaction, you have the alcohol plus you have the carboxylic acid character, and they respond together, and here you have them linking up. So the hydrogen is lost in the OH group, is also lost. They form 3 molecules of water. That's why you have the 3 plus H2O here. So there's that linking. And this condensation reaction can be done with enzymes. It can be done with other components, you know, perhaps. Sometimes you can have base catalyzed reactions, things like this. Sometimes, you know, you may have different types of substrates involved in order to make this kind of reaction occur. This is a synthesis reaction because we had two smaller types of molecules that have combined into one larger one. So the thing that's really important here to know is that this is oil, this is an ester, and what type of ester? It's a triglyceride. So this is really interesting because we know about triglycerides in our body. In fact, that's one of the things that is measured usually in a standard blood panel. Whenever you get your blood drawn to assess how your body might or might not be performing to the level that you would expect. So triglycerides are commonly found in our bodies, and this is then a form of an ester. And esters are polar at the end, okay? So at the head group, if you want to call it that, this definitely has polar character. But again, the long chain non-polar character tends to dominate in this molecule. And so what is the dominant intermolecular force then in these triglycerides or these esters? It's going to be the London forces, also known as van der Waals or dispersive forces. So those are going to be the types of interactions that you can expect to be dominant. So we're looking here, again, I just circled the range of the carboxylic acid being converted to the ester. You can see how you still have the two oxygens, which are very important and obviously, key in the functional group of both carboxylic acids and esters. But here in the carboxylic acid, you have the OH, but here in the ester, you don't have just the H. All of a sudden, you have the rest of the molecule, whatever that might be. And here you have the methane group actually connected to it. So pretty neat there. So you have the carboxylic acid functional group, you have the ester functional group. You already know now about the condensation of these. If we were to go the opposite way and perform hydrolysis of this triglyceride, you can expect then to form the glycerol and fatty acid chains. So you guys are very familiar with that, hopefully by this point. This goes back to chapter 4 and 5 kind of topics. Okay, so esters are the triglycerides, and just so that you and I, everybody, so that we're on the same page, why are these important? Because these are the main component of body fat storage. So just like how glycogen in the body is the form of sugar, energy, really like the carbohydrate that is stored, here triglycerides are the main component of body fat storage. Okay, so looking at oils and waters, again, let's refresh our memory of what we had previously talked about. Oil does not dissolve in water. This is an immiscible mixture, we would call it. An oil and water would be considered an emulsion, and this would be similar to the fat in water system that exists as milk. So that would be an oil and water emulsion. And here you have some cartoons, A, B, C, and D, where we have the fat listed as the in the orange, and the water would be like this, the cyan, this like light colored blue. And you can see how if you have them just sitting, stably as is, so if you had the water and then you just added the oil initially, you would have that layer there of just uniformity, but then over time, these droplets would form because they're not going to mix very well. So you would consider this to be an amphipathic or amphiphilic, either one. And what is going on? Well, here you have the head groups. The head groups are going to be polar. We just talked about that. And they're going to have this non-polar chain. And the non-polar chain obviously overwhelms the total character, but it still provides a significant amount of interaction. And the head group, especially if it is a carboxylate group in water, it's probably going to lose that proton. In doing so, it becomes an ion that is charged. It's an ionic kind of interaction. All of a sudden, these interactions become a little bit more noticeable whenever you have one material, say for example, the oil immersed in a whole complete different material like water. Whenever I say material, that could, that obviously refers to phases, and that could be solute versus solvent, where solvent is always present in the larger amount, solute then in the minor amount. And so this always has implications for solubility in water, and this, with respect to the ionic head group, and then with respect to the non-polar tail? Well, that has implications for making grease become a bit more soluble. And let's take a closer look. So if you had the structure of oil and water, this would actually form what's called a micelle. And a micelle is oriented with the polar head groups to the outer surface, which would be in contact then with the water molecules, okay? So this micelle, which has the structure of oil, okay, in water appears as such where you have a nonpolar center, okay? And all that nonpolar center is rising from that nonpolar tail. You have enough of these individual molecules, they align themselves, they form these spherical shapes. Again, spherical shapes are generally preferred as that's one of the lowest energy structures, geometries actually, that exist in nature. And so, you know, this is like, for instance, that's why you have a sphere instead of a square or a rectangle or triangle or, you know, rhombuses, you know, all other kind of shapes, but generally will have points are going to be a little bit more unstable. So all those hot points are generally not going to be preferred as the lowest energy configuration. And especially in liquids where things are able to move around, things are going to form as the lowest energy possible structures as they can. And so spheres are then formed. So you have that, you have water as the H2O, right? And you have those molecules all going around the exterior, and they're going to bond with that through the ionic. And then because obviously water has its own hydrogen bonding capability, but it also has polar, you know, characteristics too. So it also exhibits dipole-dipole interactions. So in doing so, you're going to have these like ionic dipole or ion dipole type of intermolecular forces. And so that is one of the dominant forces that are in play if you have oil and water. And so whenever, you know, you have soaps added to water, well, micelles are created where the nonpolar nature of that soap molecule is directed obviously in such a manner that the water molecules are surrounding. So let's talk about this a little bit more. So here are some nonpolar characteristics, right? What types of molecules? Hydrocarbons, okay? Alkanes, alkenes, aromatics, cyclic structures. We had mentioned that previously. The fatty acids, what kind? Well, fats and oils. London forces typically dominate the intermolecular attractions. Now, how does this contrast to the polar characteristics? Well, you have highly electronegative atoms in the polar characteristics. For instance, oxygen, fluorine, and nitrogen, and that can give rise, for instance, to hydrogen bonding. They will typically dissolve in water, aldehydes, ketones, and ethers, and many forces influence the intermolecular interactions. Okay, so you're going to have dipole-dipole, hydrogen bonding, ion dipole, and ionic and intermolecular forces all probably vying for dominance there, depending on what the system that you're talking about. So one of the benefits here, and we talked about solubility in the previous part 2 of this webinar, but here, if we want to improve drug solubility, you can do that by creating salts. So you have ciprofloxacin here, it's a pretty common antibacterial. Nonpolar characteristics dominate, and so if we want to be able to have this, to have the best uptake and the best dissolution in the body, well, improve it by creating salts. In our body, whether it's in the stomach or even in the small or large intestine, these are highly aqueous environments, right? So if you can have the salt form created, you can take advantage of the dipole nature of water that would be in those organs, and you would have the salts then that would give rise to ions, and then you would be able to create that ion dipole interaction. In other words, better solubility. So here, if you had pseudoephedrine as is, that would be largely nonpolar, and we know this just because, you know, although there is, you know, one group here that favors the hydrogen bonding, right? You have a lot of the other nonpolar character that tends to dominate. Surely some of it will dissolve in water, but if you really want to have even further improved solubility, well, you can treat it with hydrochloric acid, right? And then you get that salt form. So in this particular case, you would have, the chloride as the anion and the ammonia species here, like the quaternary ammonium ion here will become charged. And so you would have this as the active ingredient on the listing as pseudoephedrine hydrochloride. Okay, that doesn't mean that you're putting in necessarily like a concentrated hydrochloric acid, because you may say, well, geez, that sounds quite dangerous. No, this is a salt form. Okay, you're not putting in concentrated strong acids into your body. This is just the treatment that was used in order to get it to this point. So that would be the name of that active ingredient. Where the one on the left before, as is, the pseudoephedrine was nonpolar in terms of the overall dominant intermolecular forces. Again, salt form, you have the polar molecule, and you have ion dipole forces helping to drive solubility. So let's just talk a little bit more about the stomach, because I think it's kind of interesting. We have already covered carbohydrates in chapter 6, and I told you at that point that digestion of carbohydrates literally begins in the mouth. Your salivary glands secrete enzymes that help the breakdown of all these saccharides, okay? Whether they're simple or more complex, like starches and such. Everything then processes through the digestive system, okay? So you see how you have the stomach here listed in this image. You have the pancreas, gallbladder also shown, large intestine, small intestine, appendix, you know, all that other stuff. But if we take a closer look at the stomach, we can actually get a chance to learn just a little bit more about what's going on and what kind of pH environment that it is. So there exists on the surface of the inner surface here of the stomach gastric pits, okay, that line within this mucosa. So this mucosa is really interesting. It's quite a phenomenal actually feat of just inherent bioengineering that we don't ever have to think about. We just said, well, we have stomach. But this stomach actually has gastric glands that secrete hydrochloric-like acid through these gastric pits that allow the food that we're eating to become, well, digestible. And that in and of itself is quite interesting, because you have an environment that naturally is supportive of a low acid, or I should say, you know, a low pH, you know, highly acidic environment. I think that's actually quite impressive, and it's very interesting because it is stable, right? And of course, until it isn't, like, you know, everybody probably has heard of, you know, too many spicy foods, or certain types of diets can actually favor ulcer formation and things like that. And then, you know, if you do have an upset stomach, sometimes there might be a little bit too much of an acidic profile in there. So you might have to take like some kind of salt system in order to help neutralize that. We'll talk about that more when we get into the acid base chapter. But this would be an example here where, you know, this is a healthy tissue. You're going to eat something and it's not going to cause any kind of stomach cramping or any kind of upsetness within the body. Let's just assume that it's going to work as it should. Okay, so you have the mucosa there. Underlying that is the submucosa. Then you have the rest of the muscles that are the stomach. And then you have the connective tissue, which obviously helps keeps everything relatively fixed, you know, quote unquote. I mean, things do move around, but you still have connective tissue that can keep your stomach from floating, you know, from one side of the body to the other. Okay, I know I'm being silly there, obviously, but you can see how the stomach in general is just this one massive muscle, really. And so it is a low pH environment. It does have some enzymes in it, not too many, but it does have some, but it's mostly comprised of the gastric juices, okay? It's a form of a hydrochloric acid-like system. So as we move from the stomach, which has, you know, you want to talk about enzymes, this has about maybe on the order of 100 or so. And on the left here, we list just some of the enzymes, some of the bacteria actually, and some, you know, these bacteria would produce the enzymes, for instance, that would be able to help process the food. You have here the lactobacillus, candida, streptococcus, heliobacter pylori, and the peptostreptococcus species existing within the stomach. There's not a whole bunch of them, as you can see, maybe on the order of about 100. But then as the food processes from the stomach and it enters into the duodenum, which is the initial part of the small intestine, and as it travels through the different regions, whether it's the jejunum or the ileum, you can see that there's additional bacterial species that do exist. Again, it's still not a ton. We're talking about maybe around 100 or so of species, it doesn't increase significantly until you get to the distal part of the ileum, the beginning then of the large intestine, where you actually see the bacterial species ramp up considerably. Now you're talking about a factor of 10 to the 8, and or even up to the 10 to the 12 once it gets into the full colon. So here you have a bunch of different bacteria species, the population of which starts to diversify quite considerably. In the stool that is ultimately formed, which is formed in the large intestine, it is not then surprising to have these types of bacteria that are listed here in the colon to also be present then in the stool that you eliminate, whether that's the Bacteroides, that's the Clostridium, that's the Bifidobacterium, you know, all of that is still found whenever you eliminate, so it doesn't just stay in the colon. Portion of that does follow through with the stool. And I think that that's quite you know, notable, you know, to state. I mean, this is one of those things, you know, whenever, and we haven't really talked about this a whole lot at all, but I do try to give you some incentives sometimes about, you know, the oral health part of this, but but there was a scientist who actually tried to ingest sulfuric acid in, you know, he just would drop it into, you know, a dilute amount, of course, because you can't do a concentrate or else you would have, well, you would be burning holes in your soft tissue and the whole digestive system. But he would take some drops of dilute sulfuric acid and then try to see what the output would be, and whenever he ate something, to see what kind of bacteria would actually be present in the stool, to see whether that acid treatment would actually help reduce some of the bacterial makeup. It was at this time whenever the dental caries or cavities was becoming, well, it was relatively new, but it was, you know, becoming explored and a considerable topic of discussion to say, well, maybe this is bacterial in origin, the generation of cavities in teeth. And so, you know, researchers trying to figure out, well, where are these bacteria coming from? How is this possible? And is it the same type of bacteria that are existing in the mouth as it is in your stool whenever you eliminate? And the answer to that is no, it isn't. I mean, in the colon, you have a lot of these bacteria here. I mean, you do have some of these species that are also present in the oral environment, but there's a high concentration, very high proportion of the bacterial species that exist in the colon that are then in the stool, and not so much, you know, from the oral environment. And you could easily see that, I mean, as food, as drinks, whatever, even your natural saliva as you swallow, as it goes through all these digestive pathways, you can see that, you know, there's going to be some different pH changes. There's going to be different presence of bacterial species. Your body will also be able to produce some enzymes, as well as some of these bacteria that just that inherently reside there. So what is the pH then within the small intestine and the large intestine? Well, it slowly goes from you know, a pH around 6.4 to maybe up to 7.4. So it's a fairly neutral environment, as the bolus, you know, whatever is left over from the food that you eat that's passing from the highly acidic stomach chamber, as it passes through, the pH starts to increase to a more neutral kind of environment. Now, just to let you know, so let's go back and talk about triglycerides. Within the large intestine, this is where often lipolysis occurs, the hydrolysis of triglycerides, and it does that via enzymatic action of lipase. Okay, so lipase exists within the large intestine, and whenever this hydrolysis of the triglyceride, which is an ester, when that occurs, then that hydrolysis of an ester forms alcohol and carboxylic acids. So it's not surprising then that you would form, as we mentioned at the beginning of this webinar, the glycerols and fatty acids. So for instance, what type of glycerol? Not everything is the same, right? You have these monoacyl glycerols, you have glycerol itself, you have maybe diacylglycerol. You know, you have different types of glycerols, but they're all pretty much common in the fact that they have the alcohol functional group, the OH functional group. And you also get a series of different fatty acids, including, for instance, stearic acid. So that could be one of the fatty acids that is produced during lipolysis, whenever you're digesting fat molecules. And this obviously varies considerably. You probably didn't know we were going to talk about a cow, but I think it's quite interesting to compare the human digestive system, at least with respect to the stomach, of our own being relative to that of the cow, of this additional, you know, mammal, I guess. So you have 4 different chambers. You have the rumen, you have the oomycem, the oomycem, and the reticulum. So you have all these different chambers. Well, what are they responsible for? And I think this is quite interesting. So in the rumen, the food generally is going to be highly starchy stuff, right? Lots of polysaccharides, going to be a lot of cellulose and things like that. That's what cows like to eat, straw, things like this. It's going to be chewed, it's going to be regurgitated, and microbes are going to be introduced. This is in the rumen, okay? So that's where the digestion is going to first start. Then it'll be introduced into the reticulum, where there's actually a more, I don't want to say a tougher environment, but it's definitely more robust. So it's going to have, this is where the acids are going to be introduced. This is where you're going to have other types of microbes that are going to be able to get in there and try to work on the tougher material that wasn't able to be broken down efficiently in the rumen. In the oomycem, here you have the moisture that is going to be absorbed, right, from the bolus, and so now you're starting to form a bit of that, what's going to end up ultimately as stool-like material, and then right before you passes through, and the cow's going to continue on to process that food ultimately to completion and then elimination, there's going to be some additional enzymes that are going to be introduced in order to break down the rest of whatever that bolus has been introduced from the oomycem. And I make a note here that this is going to be most similar to the human stomach in terms of the actual concentration of the bacterial species and the enzymes present. That's where that's going to end up. So those are the 4 different chambers, and so now you probably know a little bit more, perhaps, about stomach chambers than what you thought you would talking about this. So here's another interesting aspect. So we're going to go back to the soaps and the grease because this is important. And now this is what you had done as well in your laboratory where you made soap. Okay, so you use fatty acids. Here, stearic acid is an example. What did we use? In our particular example, we used coconut oil. Coconut oil has stearic acid in it. What else did we use? We used sodium NaOH, right? Sodium hydroxide. So that is an alkali. You could use other things too. I mean, potassium hydroxide, you can have potassium carbonate. These other alkalis can also be used. And that combination of those will lead to the soap formation. So in this particular case, we would consider that to be base catalyzed because sodium hydroxide is a base, and it was a saponification reaction because we actually formed soap. So hence the saponification moniker there. So we did that in lab. And then here was an example of the sodium stearate, right? So this is a long chain, generally going to be nonpolar in that chain, but then you're going to have that polar head group. Why? Because of the ionic interactions. Right, so let's go back and let's think about, well, if we had a micelle, because soaps and water forms micelles, right? This is the general shape where you have these polar head groups making surface contact with the water molecules, and then you have these non-polar regions that would be more appealing to washing out grease and stuff, and particles, fatty particles, whatever that might be, directed towards the center. Well, that's where then the quote unquote dirt would go. That's where your grease is going to go. It's going to be directed towards the center. So as you wash your hands, then you're going to have a lot of these non-polar regions being directed toward that fattier substance that's residing on the surface of your hand, whereas the head group, which is polar, is going to be attracted to the water. Okay, so you turn on your faucet, or if you had just a little bowl of water, even if you were to put your hands in there and clean it up, you can imagine that this would be the type of microscopic action that would be going on. So just want to make a comment here. You have the sodium hydroxide. So why didn't we use calcium hydroxide, for instance? Well, actually, that's it is also quite caustic to the body and to your hands, and so you would definitely have had to use gloves for sure in order to to use that. But more importantly, the calcium would react with stearate, and actually two of the stearate molecules would be ended up bonded together or linked up with the calcium with any given calcium ion, because it's a calcium +2 charge relative to sodium, which is just the +1. So it's like a 1-to-1 ratio of the stearic acid to the sodium. Here, if you have the calcium, it's going to be a 2-to-1 ratio because the charge on calcium is 2+. So calcium stearate, commonly found as a grease, okay? And this is also one of the materials that it can start to form soap scum as well. And we actually talked about that with the hard water. So it can form scum, but it's also a very common grease. So it can be used as a lubricant in ball bearings and stuff. It can be used to help any kind of material slide against itself, usually metallic, or any kind of friction-based environments where it's going to be pretty repetitive. You can use that kind of grease. So here is an example then of the calcium stearate reaction. I show you with the calcium 2+. I give you the stearate molecule. I just bent that a little bit, right, to try to show that it doesn't have to be a linear chain like I showed up here with the sodium. But you still have this kind of reaction that would occur, and I talk about it even being used with respect to foods. You can look at some foodstuffs will contain calcium stearate, and you might think that's nasty. Well, it is what it is, but that same material can be used as a surfactant, and it also has lubricants, and it's also the main component of soap scum. So pretty interesting. So now comes the question of asking, well, what happens if you don't use, like, for instance, a bar of soap, but you would use liquid dishwashing detergent? What are the differences there? Well, soaps tend to react with hard water, right? So, like, for instance, sodium ions are typically replaced with calcium ions if your water is hard and it hasn't been softened, okay? Calcium and magnesium are two of the most common hard, quote unquote, hard ions that are just inherently found in water supplies, whether that's well water, whether that's artisanal springs that pop up, or whether that's community water. So that's typically what you're going to find. Hard water is essentially a fact of life, and wherever you go throughout the entire world, you're going to generally have calcium or magnesium in your base, in your basic supply of water that you're sourcing. Now, detergents, these are a combo of surfactants, and these are a lot less likely to react with hard water. So for instance, here's an example where you have this sulfonate species, right? And there is this aromatic component of this detergent. And again, you can see how there's a huge amount of non-polar character. You got this aliphatic chain, right? It's a long carbon chain. Then you also have the aromatic feature, and then it becomes polar, right, at the head group where you have that sulfonate species. It is charged, and it'll be in salt form, and it'll have sodium there. When immersed in water, then that's going to easily break up. You're going to get the ion dipole interactions with water. That's obviously a strong intermolecular force, so you're going to be able to get cleaning through that way. How does the dirt or grease or grime or whatever it is get resolved from, say, I don't know, clothing, or even from a dish? Well, unless it's really nasty, unless it's a very sticky substance that's going to require a little bit more elbow grease, I guess, if you will, you're going to have the non-polar regions of the detergent interacting with that dirt aspect, and of course it'll then be able to be rinsed away through the head group's interaction with water. How? Through the ion dipole interactions. Another particularly famous, I guess, surfactant, sodium lauryl sulfate, or sodium laureth sulfate. So there are some subtle differences here. One of them, obviously, being with the sodium lauryl sulfate, is that there's a long, like, ether-like kind of setup here where N is the number of chains of these. And so sodium lauryl sulfate has typically been added to many different types of ingredients. You'll see this in toothpaste, you'll see it in shampoos, you'll see it maybe in certain dish liquids. This is what really gives rise to that huge foaming action, right? The bubbles are just massive. It's a lot easier to get foam and bubbles using surfactants, generally speaking, because they're very long chain molecules. And these are commonly used In fact, I've even used sodium lauryl sulfate. I use a teeny tiny bit in order to functionalize a calcium phosphate system in order to be able to make that preferred system in order to interact with fluoride. So I have, with some of the toothpaste products that I've helped to improve, right? To make better, I combine a beta tricalcium phosphate phase with the sodium lauryl sulfate molecule, very low quantity. I mean, much low. We're talking about less than 0.02% is what I needed to be able to, to make this happen, to make this hybrid calcium phosphate structure more active for better remineralization properties in the mouth. That's obviously a side discussion there, but I have experience with that directly. Sodium lauryl sulfate, some of these detergents have been used as a possible mechanism for reducing harmful bacteria, even in the mouth. So this is going back a number of years, probably at least 40 years, whenever studies were done to see how well these surfactants could actually limit the action of bacteria, pathogenic bacteria in particular in the mouth from causing any kind of cavitations. And they do work to some degree, but not nearly as well as fluoride, for instance. So, and with a lot less effort too. So getting to have fluoride as the premier anti-cavity agent, really helps out because not a lot is needed relative to the amount of detergent that would be needed. Plus, obviously, some people may have sensitivities to these very strong ion dipole intermolecular forces that do develop whenever these detergents, essentially, these are detergents, these surfactants are introduced into the very delicate oral environment. So there are valid concerns for having too much of that, and that's why many manufacturers will even say that they have SLS-free type of products, cleaning products, hygiene products, whether that's toothpaste or even laundry detergent or even, soaps. So they're very interested in saying that they have something that might be SLS-free. But don't let that fool you, because not all of those claims in any given product are looking for all types of surfactants like this. So one may not have sodium lauryl sulfate, but it still might have sodium laureth sulfate, or it might have another comparable surfactant that may still provide soft tissue irritations, or even irritations on your hand too. I'm including that. Anything that's going to contact your skin as well can also cause those irritations. But there's a whole class of these surfactants. It can get quite big, but there's a lot of research into this. I mean, this is what some of these manufacturers do. They try to research innovative surfactants to try to clean better, right? Everybody wants more bang for their buck, if you will. And so we all want something that's going to clean relatively well. Anyway, the point is that soaps and detergents, at the end of the day, they both act to what we call emulsify the grease or dirt during the washing. So if they are able to surround it with the non-polar regions attracted to the dirt molecule, and you have the polar head groups obviously making contact with water molecules, then emulsification has been performed. The ensuing micelle that has been created can be washed away. You have a clean environment. And just to let you know, this is just an interesting tidbit that could be interesting. If you're ever going to wash your body, you try not to use detergents as much because they're generally harsher to the skin. I just mentioned that, but one of the reasons is because you're not actually producing any kind of glycerin-like kind of molecule, whether it's glycerin, whether it's another alcohol-based molecule that tends or that could have soothing effects on the skin, I guess skin friendly, if you will. So let's go back though and talk a little bit more about stearic acid, because I think that this is kind of interesting. So if you ever see tallow, if you ever heard of the term tallow, this is regarding animal fat, okay? And animal fat, if I have to show you this this chart here, I have all these different fats listed, right? You see it: tallow, coconut oil, palm kernel oil, laurel oil, olive oil, and canola oil. And all of these different types of oils, now that I'm telling you that tallow is specifically animal fat, That can also, you can also lump in human fat into that as well. So I'm not trying to be morbid, but that is the truth, right? So you have animal fat. We are a type of animal, right? We are mammals too. We have stearic acid and our fat makeup. And if you were to look at the different types of fatty acids that are present in these different types of fats, you're going to see that it's going to vary considerably depending on if it's an animal fat or if it's going to be a plant fat. And obviously not all plants have the same fats. Like if you look at olive oil, for instance, there is no lauric acid, no myristic acid. It does have some palmitic acid, a little bit of stearic acid, a lot of oleic acid, and some linoleic acid, okay? So I think that this is really interesting because if you go back up and you look at tallow, right? Tallow is pretty much evenly distributed with palmitic acid, stearic acid, and oleic acid. So the type of animal fat is generally going to have a greater distribution of these carbon-16, carbon-18 chains of fat. So you have saturated carbon-18 fatty acids, that's the stearic acid. But if there's only one that's unsaturated within that 18 carbon system, then that's oleic acid, and it has a fair amount of that. Coconut oil, right? We use coconut oil for making the soap. This one did not have a lot of stearic acid. It did have some oleic acid. It had a lot more lauric acid and myristic acid, and that's enough to be able to actually get that soap to set up. Palm kernel oil, you also have a good deal of saturated lauric acid, fatty acids, right? Myristic acid is also present. You also have some oleic acid. So anyway, there's a bunch of different acids, and you guys know that the different oils also give rise to different cooking environments too. So some, or even salad dressings and stuff. So you wouldn't necessarily use coconut oil in your dressing if you're going to have a salad, right? You would probably use something like olive oil, something that would have maybe a high degree of oleic acid character. You can see that coconut oil does not have a lot of oleic acid or even just linoleic acid. In fact, it's quite dense. So you're getting into these carbon 12 and carbon 14, and some of the stuff is it's just not going to necessarily taste as well as what you might like to put on a salad. Not that you couldn't do it, but these are just some of the different options. Just like how canola oil is sometimes used in cooking. Well, here they use this triunsaturated linolenic acid. Okay, again, it's another type of the C18. So C18s, the fatty acids can be oleic acid, linoleic acid with diunsaturation, or you can have triunsaturated linolenic acid. So it's kind of interesting. You have this dichotomy there of, well, you know, what are we going for? Are we going for functionality, or are we going for taste profile? So all of that, you know, contributes to whether you're going to use one oil or another. But anyway, saponification. Okay, so if you were to combine triglycerides, remember, I'm telling you that tallow is a type of animal fat, and we ourselves are a type of animal, obviously. The triglycerides is that form that is the storage fat in our bodies. So this is one of the reasons why you can use animal fat or human fat, mixing, and I know this is morbid, but you know, combining that with lye, which would be the potassium hydroxide or even sodium hydroxide, you can actually create the soap. What ends up happening is that you have these esters, which are the triglycerides. They become hydrolyzed, and you create glycerol, which is soothing and nice. It has a great feel, right? That's going to be moisturizing to your hands. But then you also have these fatty acid salts, and these fatty acid salts are really driving the removal of that dirt or grease or whatever you have, you know, that you want to get rid of. You know, it could be even dead skin, for instance. It could be a bit of infection if you wanted to get something clean first, right? So you would use the, you know, the non-polar feature of those fatty acids would be attracted to that, like the dead skin, the dirt, the grease, the grime, and of course that polar head group of the fatty acid salt would be attracted to the water. The micelle would form. You'd be able to rinse that away. So I'm hoping that that's all pretty much clear. You know, I give this example where you have sodium stearate, fatty acid salt, and glycerol, and of course, this all comes back to what you've already done in making soap. So this has been quite an investment of different things to talk about. You know, I think that let's talk a little bit more about triglycerides, okay, with respect to dietary lipids, because I think that this is important. So, you know, the lipids, you know, fats, you have oils, you know, here's the oils with the unsaturated systems. You can see that, that in this particular example, you know, if you have a lot of saturation, then these tails are going to be held closer together. It's going to be more likely to have more of a solid phase fat molecule. So if you can think of, I don't know, like the saran cling wrap, right? That easily wraps around itself, and you can get nice films of that. It's going to be a solid film. That would be akin to having, for instance, this fat version as we are familiar with it, where it's going to be a solid. With respect to the oils, all of this unsaturation kind of makes things a little bit, well, just flaky a little bit. You know, things can't be relatively well stacked and compacted, so it's going to have a little bit more freedom. Then you're going to then tend towards a more liquid-like phase. And so this would be your olive oil, for instance. So animals and synthetics are generally going to have the fats. Vegetables and plants are going to have these oils. This isn't unsurprising at all. I want to talk more about lipids, so we can talk about it with respect to steroids. So mainly, these are nonpolar, okay? Here would be the steroid nucleus, and you see 4 cyclic structures, all kind of connected together here. And yeah, there's some parts of it that are going to share, and that's just the properties of the steroid nucleus. So cholesterol, for instance, has additional aliphatic character on one end. So you can see around that like cyclopentic, structure on the upper right side of that steroid nucleus, and you also have the alcohol group right attached in the bottom left of that cholesterol molecule. So you can see how you might have a large amount of nonpolar character. You have a tiny amount of polar character here through the hydrogen bonding. That's what you would consider that to be, and you would consider that cholesterol to be an amphiphilic molecule. Well, what about testosterone? Testosterone also has a very similar looking steroid nucleus, so testosterone is a form of steroid, right? And it has, again, a nonpolar region, and it also has the hydrogen bonding like region. In this particular case, the OH is in the upper right-hand part, connected to that, cyclic structure with the 5 carbons there, and you have the carbonyl at the very tail end there. That's really not. I mean, it is polar to the degree where it can, have dipole-dipole like interactions, but they're not nearly as strong as the hydrogen bonding. But it still has some polar activity. You have anabolic steroids, which are basically, synthetics or analogs of the testosterone. You can see that there are some similarities, and again, you see that the steroid nucleus is pretty consistent, whether we're talking about cholesterol, testosterone, anabolic steroids, or even finally estrogen. And you can see how instead of having the carbonyl, right, that you have in the testosterone molecule, instead of having that carbonyl, and you have a little bit more, electron sharing, right? You have this like a rather full benzene ring structure here. The aromaticity is quite significant in the estrogen molecule. You have then the hydroxyl group that's also attached. So you have additional hydrogen bonding that's present. So the differences between testosterone and estrogen maybe molecularly look like they might be subtle, but they're enough to change the type of intermolecular forces that could be experienced, whether they're dipole-dipole interactions for testosterone via that carbonyl there, or whether they're, instead of dipole-dipole, hydrogen bonding interactions there in the estrogen molecule. So these are also known as lipids, and I think that, or hormones, I should say. And so what we're going to do, we're going to break for now, and then we're going to close out this whole section talking about phospholipids and where they might be found. So stay tuned for that. That'll be in part 4. We just finished part 3.